Welcome to the web seminar, Vehicle Thermal Management Modeling Using System-Level Fluid Simulation. This is presented by Andrew Hintz of Mentor Graphics Mechanical Analysis Division. If you have any questions during the presentation, please do type them into the question window and these will be addressed at the end of the presentation. I now introduce Andrew.
Thank you. Today's session will discuss 1D system-level fluid simulation and focus on vehicle thermal management of a traditional internal combustion engine system. A steady-state analysis will be used to conduct a water pump sizing study for the coolant system. To carry out this study, the variable parameters functionality within Flowmaster will be utilized. After that, the coolant system will be expanded to include the transient thermal effects of the lubrication system and the air side during a drive cycle. A radiator sizing study will be conducted to find a radiator which will adequately cool the fluid during the drive cycle. To place Flowmaster and 1D system simulation into a more broad context, 1D system-level fluid simulation has particular application in the automotive industry for vehicle thermal management when predicting how fluid systems perform. Controlling the system temperature has a major influence on performance and efficiency requirements. The competitive development of new products with both mature and continually developing technologies such as hybrid and electric vehicles continues to drive the need for upfront, fast virtual simulation. This allows more design iterations to be explored earlier to avoid further downstream costs in testing or design alterations. Mentor Graphics provides 1D and 3D computational fluid dynamics software tools suitable for a variety of industries and applications. Flowmaster software from Mentor Graphics is a 1D system fluid simulation software designed to allow engineers to quickly predict variations in flow rates, pressures, and temperatures throughout a fluid system both in steady state and transient scenarios. Flowmaster V7 Automotive can be used whether the internal fluid flow being simulated is incompressible, compressible, or a refrigerant. In the automotive industry, typical simulations Flowmaster is used for are engine cooling, airside, lubrication, fuel, exhaust, and air conditioning. Hybrid electric vehicle modeling is becoming increasingly typical, specifically in using Flowmaster for battery cooling. With built-in libraries of components specific to the automotive industry, built-in pressure drop performance data based off the published works of D.S. Miller, and fluid properties including the NIST database, it's possible to model different vehicle fluid systems and configurations. In today's webinar, productive simulation techniques and the capabilities of Flowmaster will be discussed in further detail in analyzing an engine cooling model. When running a steady-state analysis, the primary objective is to study pressures and flow rates in the system. A constant temperature will be assumed for the fluid at all points in the system. For incompressible fluids, this also means that a constant density and viscosity is assumed in the system. The benefit of running a steady-state analysis as opposed to a transient is speed of simulation. The steady-state analysis will run very quickly and allow engineers to run more what-if scenarios in a short amount of time. Here is an example of what a coolant network might look like. From the water pump, some fluid goes through the hydraulic oil cooler and the rest moves through the engine block. It's then split between the thermostat and the heater core. Fluid moving through the thermostat will either be directed through the bypass or to the radiator depending on the fluid's temperature. In a steady-state scenario, the thermostat can be modeled as two separate valves, as seen here, for manual control over the fluid path. Heater-cooler components are used in the network as a simplified version of our primary heat exchangers, specifically the radiator, heater core, and oil cooler. At this stage, thermal behavior for these components is not going to be modeled, only the pressure losses associated with them. To characterize this, The heater-cooler requires a flow area and either a loss coefficient or a pressure difference. In this case, pressure drop versus flow has been added to each one to characterize its losses. Data entry for the pump requires a bit more information. Information for the pump's rated flow, head, speed, and rated power or efficiency need to be entered. Frictional torque can be added to model the friction caused by pump rotation. For steady-state analysis, an initial speed will need to be added to define the rotational speed of the pump for the simulation. Finally, a Suter curve will need to be added to characterize the pump's actual performance. The Suter parameter is a non-dimensional performance curve which converts the pump affinity laws to a form more suitable for computational analysis. The parameter can be used to describe the variation of head or torque with flow rate and rotational speed. There is a special feature option in the catalogs to allow the user to create this curve. This special feature will allow the user to input flow versus head data similar to that a manufacturer might normally supply or can be obtained from testing, then convert to a Suter parameter by simply adding a reference point for flow rate and head. Typically, this reference point will be associated with the rated conditions for the pump. An example of when a user might utilize Flowmaster Steady-State Solver might be to try different pumps in their system to see which one best meets a design criteria. Steady-state simulations would be used to quickly and easily analyze the effects of using different pumps in the system. For a typical automotive cooling system, the criteria might be to ensure that the radiator gets somewhere between 4 and 9 gallons per minute when running our vehicle at standard conditions, and then also ensuring 15 to 20 gallons per minute through the radiator when the vehicle is running at higher RPMs. To test the system at the highest flow demand, the heater valve will be open during these simulations. Flowmaster's variable parameters function can be utilized to help speed up the time between simulations. A user might add variables to the pump's data entries, enabling them to readily change the pump's parameters to reflect the 3 different pumps previously mentioned. To add these variables, a user needs only to use the square brackets in any of the data fields and type a meaningful name between those brackets. In this specific study, only the pump's data will be varied between simulations. But once created, a variable parameter can be used for the same parameter in any number of different components in the network. To track the effects of changing the pump's input parameters and to measure against the design criteria, an output parameter can be created for the component being used to model the radiator. Right-clicking on a component will reveal the Create Output Variable feature, which allows users to provide the parameter with a useful name, then select the parameter from the list of the component's results. After running these simulations, it can be seen that pump number 2 overshoots both the standard condition and high performance target. Pump number 3 will satisfy the standard condition target, but not the high performance target. Pump number 1 satisfies both criteria. In addition to providing pressure and flow results as seen in the previous simulation, transient heat transfer simulations will allow for the modeling of thermal energy being added to or removed from the system, as well as the varying of fluid properties as a function of temperature over time. This simulation type can account for the dynamic nature of thermostats, electric fans, varying pump speeds, varying engine loads, etc. This is typical for modeling startup, heat soak, and drive cycle scenarios. For a better picture of the various transient thermal interactions, the model has been expanded to include cross-flow paths for the heat exchangers. On the air side, a stagnation pressure source has been used to account for vehicle velocity when calculating the boundary pressure. A couple heater-cooler components are also in the airside circuit to model additional heat gains from sources such as the charge air cooler and condenser. A fan is also included to move air across the radiator. A simplified oil loop is constructed to better model the dynamic heat load generated by the lubrication system and rejected into the coolant via the oil cooler. The cabin side allows for the modeling of any heat removed from the coolant by the heater core. Although the study discussed later on will assume the heater valve is closed, this circuit is set up to model the cabin controls a driver or passenger might have, including an adjustable fan speed, an option to recirculate air, a controllable heater valve, and an AC switch modeled as an evaporator heat load. The cabin volume itself will calculate a mean temperature over a characteristic length and is capable of estimating cabin comfort and reporting it in the form of percentage of people dissatisfied. In a vehicle thermal management network such as this, components such as the fan, thermostat, and engine block have additional functionality to model their real-world equivalents. The engine component can be used in both steady-state and transient scenarios. The added benefit comes in transient scenarios where this component accounts for the thermal inertia of the engine block itself. This way, the engine will warm up or cool down depending on the starting temperature and the heat flow rate. The heat flow rate represents the heat rejection from the engine, which can be entered as a constant value, a 2D value versus time, or, as will be discussed later on, control logic can be used for higher complexity. For example, the thermal duty can be input as a function of both engine rotational speed and engine torque. The thermostat reads the temperature of the fluid and adjusts the radiator valve opening according to user-defined curves. Then it adjusts the bypass route inversely. If the radiator is open, the bypass is shut, and vice versa. The performance of the thermostat can be defined by inputting two curves, one for valve position versus temperature as the fluid temperature is increasing, and one for valve position versus temperature as the fluid temperature is decreasing. Alternatively, one curve can be entered as well as a hysteresis value to define the thermostat's behavior. An alternative thermostat is available in Flowmaster, which models more detail regarding the thermostat's behavior. In addition to the temperature affecting the valve opening, the pressure difference on either side of the valve will also affect the opening. Additionally, the loss coefficient across the valve will be affected by both the valve's position as well as the flow rate through the opening. If this data is not available, it's recommended to use the basic thermostat as previously mentioned. The inputs for that component are more simplified. Similar to the pump component, the fan component represents the pressure rise versus flow rate in the system. In the case of the fan, the user enters their data for pressure rise versus flow rate and power versus flow rate, as well as the design point at which that data was collected. As the rotational speed and fluid density change, Flowmaster will extrapolate additional performance data based on the fan affinity laws. For a dynamic response, the fan component can be connected to a fan drive component, which will read the temperature of the coolant at a point in the system and convert that temperature into a rotational speed based on a user-defined curve. Much like the thermostat, this component's behavior can be defined by two curves, one as a function of rising temperature and the other falling temperature, or one curve and a hysteresis value. One further step in building up a solution to best demonstrate the dynamic interactions of the various fluid systems will be to add a master controller component. The master controller has no physical connection points, but it does contain a number of generic inputs for real data, 2D curve data, or 3D surface data. These generic inputs can be used to house data for a drive cycle simulation. As seen here, this data could include vehicle velocity versus time, which will affect the airside flow, engine rotational speed versus time, which will affect water pump rotation, oil pump rotation, as well as the engine heat load, engine torque versus time, which will also affect the thermal load of the engine, and finally the engine heat rejection as a function of both engine torque and engine rotational speed. A custom script is then written and added to read these data curves and distribute it to specific points within the system. At those specific points, controller components are used to receive the data. These components are given custom and unique titles which can then be referenced as destination points in the previous master controller script. Configured in this manner, the master controller storing the drive cycle data delegates information appropriately to the system. Because all the drive cycle data is centrally stored in the master controller component, adjusting for different drive cycles can be done easily at one component rather than at each component of interest. While the simulation is running, gauge components can be utilized to monitor results at discrete points within the system as they are being calculated. Results such as temperature, flow rate, pressure, valve position, and pump rotational speed can be monitored. Setting data for the plot window number will associate that gauge's result with an object window during the simulation. Providing a plot window title will add an appropriate legend entry to that window. The system can now be tested for different engineering criteria. A hypothetical scenario might be to try different size radiators to meet the needs of our system. The parameters of this scenario will be that a modified SFTP US06 drive cycle is used. The ambient temperature is 86 degrees Fahrenheit, assume a closed heater valve, and the goal is to find a radiator such that the system maintains a fluid temperature of roughly 200 degrees Fahrenheit without exceeding 220 degrees Fahrenheit. Flowmaster's heat exchangers are based on the steady-state energy balance equation, which states that heat duty is the heat lost by the hot side, which will equal the heat gained by the cold side. This can be characterized by setting a constant thermal duty, a hot stream temperature drop, a cold stream temperature rise, a fixed heat transfer coefficient, or a fixed effectiveness. Alternatively, to characterize a heat exchanger more dynamically, performance data can be added in the form of effectiveness as a function of both hot and cold side mass flow rate, or volumetric flow rate, heat transfer coefficient versus hot side mass flow rate and the cold side mass flux, effectiveness is a function of the number of transfer units and the specific heat ratio between the hot and cold side, or as Nusselt number versus hot side and cold side Reynolds number. Typically, a heat exchanger's thermal performance will be a function of the hot side and cold side flow rates. Standard sources for this type of heat exchanger performance data are from bench test data, where test points are obtained from a controlled experiment rig, from the manufacturer directly, typically from their own bench testing, from literature, which can provide an equation relating thermal performance to flow rate, or from 3D CFD simulations. Furthermore, regarding obtaining component-level performance data from CFD, Mentor Graphics provides a CFD product called FlowEFD. It's a concurrent 3D CFD tool which is available fully embedded in CAD tools such as CATIA, Creo or Pro Engineer, SolidWorks, and Siemens NX. It has been developed to be an accessible and accurate CFD tool for engineers with different levels of CFD expertise. Operating within the MCAD environment and with features designed to minimize traditional CFD time overheads in meshing and setup, this tool allows for significant productivity improvements for engineering departments in evaluating designs, fluid flow, and heat transfer performance earlier on to make better decisions. Within FlowEFD, component performance data can be obtained by running a parametric study across a range of operating conditions directly in the CAD model. The results of this parametric study, done by FlowEFD, can then be used in Flowmaster as an input performance data file. For the test case presented earlier, 3 radiators might be considered for use in the system as seen here: a low quality, middle quality, and high quality one. Of course, the higher the quality of the radiator, the more expensive it will be, so in addition to meeting the engineering criteria, cost must also be considered. The results of the first low-quality radiator show that the fluid temperature crosses the 220-degree threshold. This radiator should be rejected as it could lead to engine failure. The mid-grade radiator keeps the engine coolant at an adequate temperature, but it should be noted that it does come close to the 220-degree threshold and the thermostat is mostly fully open during this cycle. This doesn't leave much room should the engine be run harder or in hotter conditions. Further testing might be done to better qualify this particular radiator. Finally, the high-quality radiator, as might be expected, keeps the engine fluid at an adequate temperature with headroom for hotter conditions or running the engine harder. But if cost is a highly weighted consideration, this radiator may not make the cut and other options must be considered. Today's webinar demonstrated common studies using the example of a traditional internal combustion system. Using the same fundamental 1D CFD techniques as well as more specific capabilities of Flowmaster, engineers can undertake studies to evaluate the system interactions of a hybrid electric vehicle, specifically battery cooling, virtual soak tests using Flowmaster's zero-flow heat transfer capability, and of course more detailed studies of the lubrication and cabin circuits independently. Mentor also provides Flowmaster for MATLAB Simulink, which allows external communications to MATLAB Simulink. This allows engineers to design highly advanced control schemes in Simulink and implement those control schemes within Flowmaster. For advanced users, Flowmaster's software development kit can provide guidance to users as to how to use Flowmaster's available APIs to create advanced control schemes, customize inputs and results interfaces, such as virtual dashboards, as well as the creation of custom components. That concludes today's webinar.